Welcome back. In this video, we're going to look at example problems of finding slope and tangent lines for parametric curves. Let's get to it. All right, so here's our first example. We want to find the slope at t equals 3 for the curve represented by the parametric equations. And so here's our parametric equations. We have x is equal to t to the fourth power minus t squared plus 1, and y equals 2t. And so if we want to find the slope at a particular value of t for a set of parametric equations, what we first need to do is find the parametric derivative for these parametric equations. And that derivative will be in terms of t, and so what that derivative will represent is the slope at any value of t along the curve represented by these parametric equations. And so to find the parametric derivative, we need to know this formula right here, that dy dx, the derivative, is equal to dy dt, the derivative of y with respect to t, divided by dx dt, which is the derivative of x with respect to t. And so let's find dy dx. Let's take the derivative of x and y with respect to t. I'll start with dx dt. That's going to be equal to the derivative of t to the fourth power minus t squared plus 1. Now t to the fourth power, we want to use the power rule for derivatives on that. We will multiply the exponent down and then subtract 1 from the exponent. So we'll have 4 times t cubed, right? That 4 is multiplied down, and 4 minus 1 is 3, so we have t cubed. And then we also want to use the power rule for derivatives on t squared. So we'll have minus 2 times t to the first power, right? We multiply down that 2, and then subtract 1 from the exponent. 2 minus 1 gives us a power of 1. And then finally, the derivative of 1, that's just going to be 0, so we don't need to write that. 1 is just a constant, and the derivative of all constants is just 0. All right, so this is dx dt, 4t cubed minus 2t. Now let's find dy dt. Let's take the derivative of y with respect to t. In this case, we have a pretty simple derivative. We just need to differentiate 2t, and the derivative of a variable to the first power is just going to be equal to its coefficient. So dy dt is just equal to 2. Okay, so now we have dx dt and dy dt. Now we can find our parametric derivative dy dx. And so dy dx will be equal to dy dt divided by dx dt. So we'll have 2 divided by 4t cubed minus 2t. All right, so that's dy dx, our derivative for these parametric equations. Now what we want to do, in order to find the slope at t equals 3, is plug in that value of 3 for t in this derivative. And that will give us the slope at that value of t for the curve represented by these parametric equations. So what we'll have is dy dx evaluated at t equals 3 will be equal to 2 divided by 4 times 3 cubed minus 2 times 3. Right, we just replaced each of these t's with 3 because t is equal to 3. So now if we simplify, 3 cubed is 27, so this will be equal to 2 divided by 4 times 27 minus 2 times 3, which is equal to 6. So we'll have 4 times 27 minus 6. Now 4 times 27, that's equal to 108, so this will be equal to 2 divided by 108 minus 6, and 108 minus 6 is 102, so this is equal to 2 divided by 102, but now we can simplify this fraction by reducing the numerator and denominator by a factor of 2, right? Both 2 and 102 can be divided by 2, and if we do that, we will get 1 divided by 51. And so 1 divided by 51 is the slope at t equals 3 for the curve represented by these parametric equations. All right, let's take a look at another example. So next up, we have a slightly different example. We want to find the equation of the tangent line at t equals 2 for the curve represented by the parametric equations. We have x equals 5t and y equals 3t squared plus 9. Now this example is different than our previous example. Instead of only looking for a slope, now we're going to be looking for something else as well, because we want to find the equation of a tangent line at a particular value of t for this parametric curve. And in order to find the equation of a tangent line, we need two different things. We need the slope at that value of t, which is what we found in the previous example, but of course we have a different value of t and different equations this time. And then we're also going to need a point in terms of x and y that corresponds to this value of t. All right, so I'm going to make a note of that. We need two things. we need 1, the slope, and 2, a point. Once we have those two things, we can create the equation of a tangent line at this value of t for these parametric equations. All right, and so let's start with the slope. Let's find the slope at this value of t for the curve represented by these equations. And so in order to find that slope, we're going to go through that same process that we did in the previous example. We want to find the parametric derivative for our parametric equations and then evaluate it at this value of t, which is 2. All right, so let's find our parametric derivative. We need to take a derivative with respect to t of both x and y. Let's start with x. In this case, dx dt will be equal to the derivative of 5t. And the derivative of t to the first power will always be equal to the coefficient. So in this case, we have 5. And then dy dt will be equal to the derivative of 3t squared plus 9. Now 3t squared, we can use the power rule for derivatives here. Multiply this 2 down, and we'll have 3 times 2, which is 6. So we'll have 6 times t to the first power, right? Because then we're going to subtract 1 from that exponent of 2, and 2 minus 1 is 1. All right, and we typically don't write that first power, we just write t. Okay, and then the derivative of 9 is a constant, so the derivative is 0, because the derivative of all constants is 0. All right, so now we have dx dt and dy dt, so now we can find our parametric derivative, dy dx. dy dx will be equal to dy dt divided by dx dt. So we're going to have 6t divided by 5. All right, so dy dx is 6t divided by 5. And now that we have our parametric derivative, let's evaluate it at our value of t to find the slope that we will need for our equation of a tangent line. So we're going to have dy dx evaluated at t equals 2. That will be equal to 6 times 2 divided by 5. Right, we just replaced this t with 2 because t is equal to 2. So we have 6 times 2, which is 12, divided by 5. So this slope will be 12/5. All right, and so now we found the slope that we need for the equation of a tangent line. The slope at t equals 2 for the curve represented by these equations is 12/5. And so I'll write that up here. Our slope, m, will be equal to 12/5. And now let's work on finding our point. Now to find the point, we want to use our value of t, where we want to find the equation of the tangent line, t equals 2, and we want to plug that value into each of our parametric equations to get an x-coordinate and a y-coordinate that will make up a point. So let's do that. When t equals 2, x will be equal to 5 times 2, right? X is equal to 5 times t. So if t is equal to 2, then x is equal to 5 times 2. And so x is equal to 10. And then for y will be equal to 3 times 2 squared plus 9. And 2 squared is 4. So we have 3 times 4, which is 12. And so y is equal to 12 plus 9. And 12 plus 9 is 21. And so y is equal to 21. And so now we have an x-coordinate and a y-coordinate, which together make up the point at t equals 2 for this parametric curve. So our point will be the point 10, 21. All right, 10 is our x-coordinate and 21 is our y-coordinate. And so now that we have the slope and the point at this value of t for these parametric equations, we are now ready to find the equation of the tangent line at that value of t. All we have to do to find that equation is use the point-slope formula. And the point-slope formula is that y minus y1 is equal to m times x minus x1. Right, you learn about this formula in algebra. This allows you to find an equation of a line given a point and the slope. In this case, our slope m is 12/5, and our point, which is represented by x1, y1, is 10, 21. All right, so m is equal to 12/5, x1 is equal to 10, and y1 is equal to 21. So what we'll have is y minus 21 is equal to 12/5 times x minus 10. Okay, so now if we simplify, let's distribute this slope through this quantity. 12/5 multiplied by x is 12/5 times x. So we'll have y minus 21 is equal to 12/5 times x. And then 12/5 times negative 10 will be negative 120/5. Right, we multiply 12 by 10 to get negative 120, and then we're still dividing by that 5. All right, now 120 is divisible by 5. 120 divided by 5 is 24. And so we can rewrite this to be minus 24. And then we can simplify one more time by adding 21 to both sides in order to solve for y. So if we do that, we will have that y is equal to 12 fifths times x, and then negative 24 plus 21 will be negative 3. All right, and so y equals 12 fifths x minus 3 is the equation of the tangent line at t equals 2 for the curve represented by these parametric equations. All we had to do to find this equation was find the slope at that value of t and the point at that value of t, and then use that slope and that point in the point-slope formula to create that equation. All right, so for our next example, we want to find the equation of the tangent line at t equals pi divided by 4 for the curve represented by the parametric equations. And we have x equals 2 times sine t plus the square root of 2, and y equals 4 times cosine t minus the square root of 2. All right, so just like with our last example, we want to find the equation of a tangent line at a particular value of t, so we need to find two things. We need to find the slope at that value of t, and we need to find the coordinate point that corresponds to that value of t. All right, so I'll make a list of what we need here. We need 1, the slope, and 2, the point. All right, so let's work on finding those two things, and then we can create the equation of the tangent line. So let's start with the slope. What we need to do to find the slope is first find the parametric derivative associated with these parametric equations, and then evaluate that derivative at this value of t. So to find that parametric derivative, we need to differentiate x and y with respect to t. So let's start with x. We'll have dx dt is equal to the derivative of 2 times sine t, and the derivative of sine is cosine, so we'll have 2 times cosine t, and then the square root of 2, that's just a constant value, so the derivative of the square root of 2 will just be 0 because the derivative of all constants is 0. All right, so 2 times cosine t will be dx dt, but now what about the derivative of y with respect to t? Let's look at dy dt. That will be equal to the derivative of 4 times cosine t, and the derivative of cosine is negative sine, so we're going to have negative 4 times sine t, and then the derivative of the negative square root of 2 will be 0 because the negative square root of 2 is just a constant. All right, so we don't need to write that 0 on the end. Dy dt is just equal to negative 4 times sine t. Okay, so now that we have dx dt and dy dt, let's form our parametric derivative dy dx. Dy dx will be equal to dy dt divided by dx dt. So we'll have negative 4 sine t divided by 2 times cosine t. All right, so negative 4 times sine t divided by 2 times cosine t. All right, now we can simplify a little bit. Negative 4 divided by 2, that's equal to negative 2. So this will be equal to negative 2. And then it's going to be multiplied by sine divided by cosine. And if you remember your trig identities, sine divided by cosine is the same as tangent. So instead of writing sine divided by cosine, we'll just write tangent t. Okay, and so negative 2 times tangent t is dy dx, the derivative of our parametric equations. Now what we want to do is evaluate this derivative at our value of t, where we want to find the equation of the tangent line. So what we're going to do is plug in pi divided by 4 into this derivative. All right, so what we'll have is dy dx evaluated at t equals pi divided by 4, and that will be equal to negative 2 times tangent of pi divided by 4. Now tangent of pi divided by 4 is equal to 1, so this is equal to negative 2 times 1, which is equal to negative 2. So our slope will be negative 2. And so the first thing that we needed, we now found. We now know that the slope, m, is equal to negative 2. All right, and so now that we found the slope at that value of t, let's work on finding the coordinate point that corresponds to that value of t. And so what we'll do is plug this value of t into each of these parametric equations to get an x-coordinate and a y-coordinate associated with that value of t. So when t equals pi divided by 4, x will be equal to 2 times sine of pi divided by 4 plus the square root of 2. All right, we just plugged pi divided by 4 in for t in this parametric equation for x. And sine of pi divided by 4 is the square root of 2 divided by 2. So this will be equal to 2 times the square root of 2 divided by 2. And we're still adding the square root of 2 to that. And then this 2 and this 2 will cancel out, right? 2 divided by 2 is just 1. So x will just be equal to the square root of 2 plus the square root of 2. And the square root of 2 plus itself is just going to be 2 times the square root of 2, right? So x will be equal to 2 times the square root of 2. So if we start to form our coordinate point here, we know that the x-coordinate is 2 times the square root of 2. But now let's find our y-coordinate. When t equals pi divided by 4, y will be equal to 4 times cosine of pi divided by 4 minus the square root of 2. All right, so we just replaced this t with pi divided by 4 because that's what t is equal to. And now cosine of pi divided by 4 is actually the same value as sine of pi divided by 4. It's also equal to the square root of 2 divided by 2. So y is equal to 4 times the square root of 2 divided by 2, and then we're subtracting that square root of 2 on the end there. Okay, and then 4 divided by 2, that's equal to 2. So this will be equal to 2 times the square root of 2 minus the square root of 2. And 2 square roots of 2 minus 1 square root of 2 will just leave us with 1 square root of 2. All right, and so y is equal to the square root of 2 for that value of t. And so that's going to be the y-coordinate for our point. So I'll write that in. We will have the square root of 2 as our y-coordinate. And now we have the full coordinate point at the value of t for the curve represented by these parametric equations. It's 2 times the square root of 2, comma, the square root of 2. All right, and so now that we have the slope at our value of t and the point that corresponds to that value of t, we can now find the equation of the tangent line at that value of t. We just need to use our point-slope formula. And the point-slope formula is y minus y1, and that's equal to m, the slope, times x minus x1. And remember, x1 and y1 correspond to the x and y coordinates of the point that we found at that value of t. All right, so x1 is equal to 2 square roots of 2, y1 is equal to the square root of 2, and the slope m is equal to negative 2. So we'll have y minus the square root of 2 is equal to the slope, which is a negative 2, times x minus x1, which is 2 square roots of 2. All right, now if we simplify, we can distribute this negative 2 through this quantity, and we'll have y minus the square root of 2 is equal to negative 2 times x, and then negative 2 times the negative 2 square roots of 2 will be positive 4 square roots of 2. All right, negative 2 times negative 2 is 4, and it's still multiplied by this square root of 2. And then we have one thing left to do, which is to add the square root of 2 to both sides of the equation in order to isolate y. So if we do that, we'll be adding the square root of 2 to 4 square roots of 2, so this will become 5 square roots of 2. All right, so what we'll have is y is equal to negative 2x plus 5 square roots of 2. All right, we're just adding the square root of 2 to both sides of the equation, so that cancels out with this negative square root of 2, and then on this side, we have 4 square roots of 2 plus another square root of 2, which is why we have 5 square roots of 2. All right, so y equals negative 2x plus 5 square roots of 2 is the equation of the tangent line at t equals pi divided by 4 for the curve represented by these parametric equations. Okay, so here's our next example. We want to find all points of horizontal and vertical tangency to the curve represented by the parametric equations. And we have x equals t cubed minus 12t and y equals 5t plus 3. Now this problem is different than what we've done so far. Instead of just finding the tangent line at a specific value of t, we are looking for specific locations for horizontal and vertical tangent lines, which are two special types of tangent lines that we can find for a curve. And if you want to find the location of horizontal and vertical tangent lines for a curve represented by parametric equations, you need to remember the following rules. That horizontal tangent lines are located where the slope is 0, and so remember, for a parametric curve, the slope is represented by this form of the derivative, right? The derivative is the slope, and this slope will be equal to 0 when this numerator is 0, because 0 divided by anything except for 0 is 0. And so when dy dt is 0 for a particular value of t, that will be the location of a horizontal tangent line. and that is given that dx dt does not equal 0 for that same value of t. All right, and then vertical tangent lines are located where the slope is undefined, and that's going to occur when this denominator for our derivative or our slope is equal to 0, right? You can't divide by 0. That results in an undefined value. So when dx dt is equal to 0, for a certain value of t, that will be the location of a vertical tangent line. And that is given that dy dt does not equal 0 for that same value of t. All right, so there is the possibility that both dy dt and dx dt could be 0 at the same time. When that happens, that typically means that your curve intersects with itself, and you might have a horizontal tangent line and a vertical tangent line at that point, or you might just have one or the other. But that's a very rare occurrence that doesn't happen for a lot of parametric curves, and so we're not going to worry about that in this video. We're just going to focus on curves that have points where there is only one special type of tangent line, just a horizontal tangent line or a vertical tangent line. All right, so just remember that horizontal tangent lines occur where the slope is 0, so when dy dt is equal to 0, and vertical tangent lines occur where the slope is undefined, which is when dx dt is equal to 0. So if we go back to our example, let's start by finding all points of horizontal tangency, where the slope will be 0. And so let's look for those points of horizontal tangency. Let's find dy dt so that we can set it equal to 0. That is going to be equal to the derivative of y with respect to t. The derivative of 5t is just going to be 5 because the derivative of t to the first power is just going to be equal to the coefficient. So dy dt is equal to 5, and then the derivative of 3 is 0 because 3 is a constant. All right, so dy dt is equal to 5. And what we want to do at this point is set dy dt equal to 0 and solve for any values of t. But in this case, notice that there are no t's in this derivative, right? Dy dt is just equal to 5. So if we set that equal to 0, we just have 0 equals 5, which is an untrue statement, right? 0 does not equal 5. And so in this case, there are no values of t for which dy dt equals 0. Dy dt is going to be equal to 5 for all values of t. And so what that means is that there are no horizontal tangent lines for the curve represented by these parametric equations. All right, so no horizontal tangent lines. All right, so we know there's no horizontal tangent lines or no points of horizontal tangency, but what about points of vertical tangency or vertical tangent lines? Well, to find those, we need to find dx dt, and then we'll set that equal to 0. And dx dt is the derivative of x with respect to t, and so we'll take the derivative of t cubed minus 12t. For t cubed, we'll use the power rule for derivatives. We'll multiply that 3 down and subtract 1 from the exponent. So we'll have 3t squared, right? We multiply the 3 down, and then 3 minus 1 is 2. And then the derivative of negative 12t will be negative 12 because the derivative of t to the first power will just be that coefficient. So we have 3t squared minus 12. All right, so now what we want to do to find all points of vertical tangency is set dx dt equal to 0 and solve for our values of t such that that is true. So we'll have 0 is equal to 3t squared minus 12. Now, unlike this equation over here, we actually have values of t that we can solve for, right? We have 3 times t squared minus 12. So let's solve for t. Let's add 12 to both sides of the equation. We'll have 12 is equal to 3t squared. And then we can divide both sides by 3. And so if we do that, 12 divided by 3 is 4. So we'll have 4 is equal to t squared. And then to solve for t, we need to take the square root of both sides of this equation. And taking the square root of 4 will give you 2 different values. It will give you positive 2 and negative 2. And so what we find is that t is equal to plus or minus 2, right? 2 squared is 4, and negative 2 squared is also 4. So when t equals plus or minus 2, dx dt is equal to 0, which means that the slope is undefined for those 2 values of t, which means we have horizontal tangent lines at those values of t. However, we're not done yet. We don't want to just find the values of t where we have vertical tangency. We want to find the points of vertical tangency. So what we have to do is plug these 2 values of t into our parametric equations to get their corresponding coordinate points. So let's start with t equals positive 2. Let's plug 2 into our parametric equations. When t equals 2, x will be equal to 2 cubed minus 12 times 2. right? We just replaced this t and this t with 2. And 2 cubed is 8, so x is equal to 8 minus 12 times 2, which is 24. So we have 8 minus 24, and that is equal to negative 16. So x is equal to negative 16. And then for y, we're plugging in 2 for t, so we'll have 5 times 2 plus 3, which will be equal to 10 plus 3, which is equal to 13. And so the coordinate point that corresponds to this value of t equals 2, is the negative 16, 13. And so negative 16, 13 is one of the points where we have vertical tangency, or one of the points along this curve where we have a vertical tangent line. But now let's find the other point by plugging in t equals negative 2. And when t equals negative 2, x will be equal to negative 2 cubed minus 12 times negative 2. And negative 2 cubed is negative 8. So x will be equal to negative 8. And then we have negative 12 times negative 2. That will be positive 24. So we'll have plus 24. And negative 8 plus 24 will be positive 16. So x will be equal to 16. And then for y, when t equals negative 2, we'll plug negative 2 in for this t. So we'll have 5 times negative 2 plus 3. And negative 2 times 5 is negative 10, so y is equal to negative 10 plus 3, which is equal to negative 7. So y is equal to negative 7, and so our other point of vertical tangency will be 16, negative 7. All right, and so with that, we have now found all points of horizontal and vertical tangency for the curve represented by these parametric equations. We found that there were no points of horizontal tangency, or no horizontal tangent lines, and we found two values of t for which there was vertical tangency, which resulted in these two coordinate points by plugging in those values of t into these parametric equations. Okay, let's look at one more example for this video. All right, so here's our last example. We want to find all points of horizontal and vertical tangency to the curve represented by the parametric equations. And so this time we have x equals 7 times cosine t, and y equals 7 times sine t. And we also have a restriction on our values of t. T can only be values from 0 to 2 pi, including both of those endpoints. All right, so just like with our previous example, we want to find any points for the curve represented by these equations where we have horizontal or vertical tangent lines. And so let's start by finding the location of horizontal tangent lines. And horizontal tangent lines occur when dy dt is equal to 0. And so what we need to do is find dy dt, the derivative of y with respect to t, and then set that equal to 0 and solve for t. So let's take the derivative of y with respect to t. We have 7 times sine t, and the derivative of sine is cosine, so dy dt will be 7 times cosine t. All right, so let's set that equal to 0. We'll have 0 is equal to 7 times cosine t. We can divide both sides by 7, and we'll just have 0 is equal to cosine t, because 0 divided by anything except 0, of course, is 0. And now we just have an equation, 0 is equal to cosine t. And so now we just have to ask ourselves, what values of t on this interval from 0 to 2 pi will make cosine equal to 0? Well, there's only two values of t that are going to make that happen. If you're familiar with your trig functions, you know that cosine is equal to 0 at pi over 2 and 3 pi divided by 2. So when t equals pi divided by 2 and 3 pi divided by 2, dy dt will be equal to 0. All right, but these are just the values of t. We want to find the points of horizontal and vertical tangency, and so to find the actual points where we have horizontal tangent lines, we need to plug these values of t into our parametric equations. And so let's start by plugging pi over 2 into our parametric equations. When t equals pi divided by 2, x will be equal to 7 times cosine of pi divided by 2, but we know that cosine of pi divided by 2 is 0, so 0 times 7 is 0, so x is equal to 0, and then y will be equal to 7 times sine of pi divided by 2. Now sine of pi divided by 2 is 1, so we have 1 times 7, and so y is equal to 7. All right, and so when t equals pi divided by 2, our coordinate point is 0, 7. At 0, 7, we have a horizontal tangent line for the curve represented by these parametric equations. All right, so that was one of our points for when t equals pi divided by 2, but now we need to check our other value of t, which is 3 pi divided by 2, to get our other point. So when t equals 3 pi divided by 2, x will be equal to 7 times cosine of 3 pi divided by 2, but cosine of 3 pi divided by 2 is 0, so we have 0 times 7, which is 0. So x equals 0, and then y will be equal to 7 times sine of 3 pi divided by 2. Now sine of 3 pi divided by 2 is negative 1, so we'll have negative 1 times 7, which is negative 7. So the other coordinate point where we will have a horizontal tangent line is 0, negative 7. All right, so these 2 points right here are the only points of horizontal tangency for the curve represented by these parametric equations. So now that we found all the points of horizontal tangency, now what we want to do is find all the points of vertical tangency. Okay, and so to find points of vertical tangency, we need to find dx dt because vertical tangent lines occur where dx dt is equal to 0, where the slope is undefined. And so let's find dx dt. dx dt is the derivative of x with respect to t, so let's take the derivative of 7 times cosine t. The derivative of cosine is negative sine, so dx dt will be equal to negative 7 times sine t. And so now what we want to do is set dx dt equal to 0 and solve for t. So 0 will be equal to negative 7 times sine t, and then we can divide both sides by negative 7, and that will give us that 0 is equal to sine t, right? 0 divided by negative 7 will be 0, and then all we have to do now is ask ourselves what values of t on this interval will make sine equal to 0. All right, now there are actually 3 values of t that will make sine equal to 0 on this interval. That will be 0, pi, and 2 pi. And so our 3 solutions are t is equal to 0, pi, and 2 pi. All right, but we actually don't need to include 2 pi because 0 and 2 pi are actually going to give us the same point, right? Sine of 0 and sine of 2 pi is the same value, and cosine of 0 and cosine of 2 pi is also the same value. So that's going to give us the same point, which means that t equals 0 and 2 pi together only make up 1 point of vertical tangency. And so really we only need to pay attention to these first 2 values of t equals 0 and t equals pi. Okay, and so for these 2 values of t, we're going to have vertical tangent lines along our curve, but we need to find the actual points associated with those values of t. And so let's find them. Let's start with t equals 0. When t equals 0, x will be equal to 0 plugged into cosine, right? X is equal to 7 times cosine t. And when t equals 0, we'll have 7 times cosine of 0. And cosine of 0 is 1, so we'll have 7 times 1, which is 7. So x is equal to 7. And then for y, that will be equal to 7 times sine of 0. And sine of 0 is 0, and 0 times 7 is 0, so y will be equal to 0. So the coordinate point when t equals 0 will be 7, 0. All right, the x-coordinate is 7, and the y-coordinate is 0. Now just to show you that you will get the same point when t equals 2 pi, if we plug 2 pi into both of these parametric equations, cosine of 2 pi is 1, 1 times 7 is 7, so x is 7, and then 2 pi plugged into this equation, we have 7 times sine of 2 pi, sine of 2 pi is 0, and 0 times 7 is 0. So that gives us the same point. 0 and 2 pi give us the exact same point, which only accounts for 1 vertical tangent line, not 2. Okay, and so that's one of our points of vertical tangency. Now let's find the other with t equals pi. And when t equals pi, x will be equal to pi plugged into our x equation. So we'll have x is equal to 7 times cosine of pi. And cosine of pi is a negative 1. So we'll have negative 1 times 7, which gives us negative 7. So x is equal to negative 7. And then for y will be equal to pi plugged in for t in this equation. So we'll have y is equal to 7 times sine of pi, but sine of pi is 0. So we have 0 times 7, which is 0, which gives us that y is equal to 0. All right, so our other coordinate point where we have a vertical tangent line is negative 7, 0. All right, so at 7, 0 and negative 7, 0, there are vertical tangent lines for this curve represented by these parametric equations. All right, and so now we have finished this example. We have found all points of horizontal and vertical tangency to the curve represented by these two parametric equations. The only 2 points of horizontal tangency where we have horizontal tangent lines is 0, 7 and 0, -7, and the only 2 points where we have vertical tangency or vertical tangent lines is 7, 0 and -7, 0. All right, so these 4 points are all the points of horizontal and vertical tangency. All right, and so that was it for this example, and this was the last example for this video. So if you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.